Okay, so today, what I want to do, we've got really, I think, one more unit that we got to really cover. And then after that, I'm not sure, I don't think the placement tests, I don't think we're really required to do anything else. We might do just a really brief coverage of logs and exponentials, so you've seen them and you're familiar with them when you talk about them next year, but it won't be that big a deal. But this is part of the last real thing that we have to do in Algebra 2. So, rational functions. We're going to talk about rational functions. This week, we're going to really just focus on the graphs of rational functions. So we want to be able to do two things. We want to either be able to sketch a graph of a rational function or recognize the graph of a rational function. So I'm going to essentially give you mostly two kinds of questions, where you're going to be either given a graph and I want you to write the function that goes with it, or I'm going to give you a function and you have to choose the graph that goes with it, right? So just a little, and then the next section we'll do after that, we're gonna focus more on the algebra of solving equations that involve rational functions. Okay, and that's not a big deal. Okay, none of this stuff is really for you guys is going to be very hard. You have all the building blocks of knowing how to do this stuff already from earlier in the year, and so this is really just reassembling some things you already know. So rational function, definition of a rational function, ratio means fraction, right? So a rational function is any function that can be written as a fraction or a ratio of polynomials, a polynomial divided by a polynomial, okay? So f of x, if p of x and q of x are both polynomials, then their quotient would be a rational function. Okay, so the simplest rational function is a special function 1 over x. This is sometimes, we call this the inverse function, but like a lot of things in math, that's a little confusing because inverse is used in a different way than we're used to. When we talk about an inverse function, we've done a lot of stuff with that, right? That's an inverse function is a function, the function we get when we switch x and y, right, and solve for y. Okay, when we switch the domain and the range. This is different. This is different. We call this the inverse function because it's flipped. Okay, there's another reason that we do that. It occurs to me maybe I should, we'll do this. So the other reason we call this the inverse function, there's two parts of this and they kind of come together. This happens in math every once in a while. Let's find the inverse of this function real quick. So what are the steps? Well, I'm going to set that equal to y, write it in terms of y. So I get y equals 1 over x. Then I'm going to flip the x and the y, right? And so that's going to give me x equals 1 over y. And we haven't done this yet, really, but you guys could solve this problem just based on Algebra 1. What would you do if I have two fractions equal to each other? Cross multiply, right? So that's going to give me x times y equals 1 times 1. And then to isolate y, what do I get? I divide both sides by x, right? I end up with y equals 1 over x. What? How about that? Its inverse is itself. So that's another reason that we call it the inverse function. I always kind of associate it with the fact that it's a reciprocal of x. That's usually what I think people mean by it. But it just turns out that it is its own inverse also. Okay? So, interesting. What we want to be able to do here, though, is we want to be able to take this special function, 1 over x, and this is one of a handful of functions that we're going to know what the parent graphs look like. And what are they, by the way? Let's just take a quick summary of the functions that we know. Just the parent graphs. So what if we wanted to graph something like f of x equals x squared? The most basic quadratic function. What's that one look like? Parabola with the vertex at 0, 0, right? So that one just, we know what that one looks like. Vertex there, we go over 1 and up 1, backwards 1 and up 1, and it's just like that, no big deal, right? We can tweak that one. We can transform it using values of a, b, h, and k and make it anything we want to, right? We can take the parent graph f of x equals x cubed. What's that one look like? Very similar. But what's it do differently than X squared. Okay, I've seen people doing this kind of thing. That's the one that does this, right? So it's gonna go over one and up one, but then it goes back one and down one. So it's gonna do that, right? And we'd say that this is the point, this is the vertex, and that's the point that we kind of treat as a vertex, right? The point of symmetry, at least, right? What if we did absolute value function? What did that look like? And what did that look like?
It would go like, I don't know how to describe it.
It's got a real distinct shape. What's that one look like? It's been a while. No. What is it again? It's a V. Yeah, it's a V. The x squared is a u, right? A parabola is a u. The absolute value function is just a v. So we got the vertex right there, and then it's just going to do that, right? Okay. Over one and up one on this side, back one and up one on that side. But it's a v. Okay. And once again, we can tweak that any way we want to by stretching, compressing, reflecting, translating, right? And then, I guess we got two more. What about a square root? What's the parent graph of a square root function look like? Starts where? 0, 0, good. And what's it do? Yeah, it's like half of a sideways parabola, isn't it? So this is the one that's going to go like that, right? And then the last one, cube root of x. Similar, but just like up here, it's going to go both directions, right? Okay, so it's one that's going to go over one and up one, but back one and down one, and so it's going to do that, right? Those are all parent graphs that we know, right, that we've used, and we can tweak any of those. Well, essentially, we're just adding one more to the list. Here's the function that we're adding to the list. 1 over x. Okay, so let's explore this a little bit. This is a really important function. There's a lot of this comes up a lot in calculus and in science and engineering. Like whenever you're calculating, not that this is really a big deal, but whenever you're calculating like an average cost per item that you're producing, right? Or you're an average profit per item. Typically, it's going to be modeled by a function like this. And we'll see why in a second. We'll talk about the shape of this curve, and you can see why that maybe makes sense. So let's try to get a sketch of this, though, okay? So what are some points? Let's go ahead and figure out, first of all, what's the domain of this function? What are all the values of x that we could input? Let me ask it a different way. Are there any values that we couldn't input? Any values of x that wouldn't be allowed? What are the two rules we always have to obey? We can't divide by 0, right? Can't divide by 0, and we can't take a square root of a negative, or any even root of a negative. Well, there's no square root, so that one we're fine with. But we have an x on the bottom. So what value could x not have, obviously, then? 0, right? So our domain is just that x cannot equal 0, okay? Well, what's going to happen for some other values of x? What if I pick a value, what if I evaluate the function at 1? What do I get back? 1 over 1 is 1. Good, okay, so we know this tells us that when x is 1, y is 1, right? So we know it's going to go through the point 1, 1, okay? What's another one? Riley, what's another one? So if we go over 1, we go up 1. What if I plug in a value -1 into my function? What do I get back?
Go left 1 and down.
Left 1 and down 1. Good, because I'm going to get back -1. Good. So left 1 and down 1. So I get the point -1, -1. Good. So those are 2 points that the graph has to go through. Now what? Let's look at this in terms of, we could just make a t-table and just keep plotting values, and that would work. I mean, that's going to give us, and then just kind of connect the dots with a smooth curve, right? Let's do this a little different way. Let's go back and look at this in terms of some stuff that we talked about earlier in the year. This is something that's important in the next couple of years, especially in calculus. Okay, so let's talk about this in terms of a limit. We said stuff like this: as x approaches a value, y is going to approach something, or f of x is going to approach something. So we want to know the behavior of the function. Now let's think about this as x gets really big. Okay, x is on the bottom of a fraction. What's the behavior of a fraction if the top stays the same but the bottom gets really big? What's the overall value of the fraction doing? Think about it. What's it doing? It's getting small. Compare like 1 over 2 to 1 over 1,000, right? 1/2 is a lot bigger than 1/1000. So you tell me then, as x approaches positive infinity, what is the value of the fraction going to approach? 0. Does that make sense? It's going to get really, really small. If x is a trillion, it's 1/1 trillionth. Well, 1/1 trillionth is a really, really small decimal. That's very close to 0, isn't it? And if I keep going, it's just going to get closer and closer. And so as we sweep off to the right, the function is just going to get lower and lower and lower and closer to the x-axis, right? Okay, what about if we back up the other way, though? So let's see what happens. We know that x can't have a value of 0. That's not allowed, because that would force us to divide by 0, and that's a rule we can't break. But as we back up towards 0, let's try something a little different. What about as x approaches 0, can't get to 0, but it's going to approach 0 from the right. And here's our calculus notation for that. We'd say as x approaches 0 from the positive direction, right? Because we know this is the x-axis, and this is the positive x-axis, right? And that's the negative x-axis in that direction, okay? So that means that we're going to be backing down towards 0 from the right side, so we're going to go like from 1 to 1/2 to 1/4 to 1/10 to 1/1000, etc., etc., right? Well, what if I took like a really small value of x, like 1/1 billionth? What's 1 divided by 1 over 1 billion? What do I do when I divide by a fraction?
Oh, the reciprocal.
Yeah, I flip and multiply, right? So 1 over 1 billionth is equal to what?
A billionth of
No, let's look at that. 1 divided by 1 billionth. If I flip and multiply that, it's just 1 billion, isn't it? Doesn't that make sense? Doesn't 1 billionth go into 1 a billion times, right? So I'm going to get a huge number, aren't I? Right? So as x approaches 0 from the positive direction, what's the function approaching? What's going on? Look at that pattern. If I'm at 1/2, at x equals 1/2, the reciprocal of 1/2 is 2, right? So when x is 1/2, I'm going to go up to 2. When x is 1/4, I'm going to go up to 4. When x is 1/10, I'm going to go up to 10. When x is 1 billionth, I go up to a billion. When x is 1 trillionth, I go up to a trillion. As x approaches 0 from the right side, so they're positive, very, very small numbers, what is f of x approaching? It's never going to get there, but what's it approaching? Infinity. Yeah, it's approaching positive infinity. So what's the behavior look like then? Let's look at this. Is really interesting. Look what this function does. It's going to go it looks like that, doesn't it? You see that? We know it goes through the point 1, 1, but if I continue to the right, it's going to get closer and closer and closer to what we call a horizontal asymptote at y equals 0, the x-axis. Okay, so this is that line right there. Y equals 0 is a horizontal asymptote. All that means is, as we go really far off to the right, the function is just gonna start to stick to that asymptote more and more closely. Does it ever get there? No, it doesn't. And let's go back to the discussion we had earlier in the year. Sometimes when you look at these again after a while and your brain's processed, things start to, oh, now that makes sense. So what if I were to, this is limiting behavior. If I'm gonna cut my distance to the door in half every second for the rest of eternity, do I ever get to the door? Mathematically, I don't, right? I never get to the door. There's always gonna be, my steps get smaller and smaller and smaller each time, and at some point they get ridiculously small, but I never get there. Okay, here's the question I asked you earlier in the year. Remember this? What if we had an infinitely fine Sharpie? We had a Sharpie that could make a dot that was literally the size of a point, which has no size at all, okay? Is there any point, I can't cheat and make a point on the door, but is there any point on the floor that's not actually physically on the door that I could make on the ground that I wouldn't eventually step on? You see what I'm saying? So can I get down there with my really fine Sharpie, and can I make a point on the floor that eventually I wouldn't step on if I'm cutting my distance to the door in half? There isn't, is there? Because you might be thinking, well, that's easy, just make the point next to the door, duh, right? But if I get a more powerful microscope and I zoom in, then that point, I can see that there's actually some more points between that point and the door. How many points? Infinite. So maybe I say, okay, now I got it. This time I'm going to pick the point next to the door. Zoom in. There's an infinite more points, right? There's no limit to the number of times that I can zoom in mathematically, right? And so I'd never get there, right? The same kind of thing is going on here, this asymptotic behavior. It never actually gets to y equals 0, but it can get arbitrarily close, is what we'd say in math. There's no value of y that's too close to 0 for me to eventually get to, right? And then the same behavior is going on here. What do you suppose we call this asymptote? Not a horizontal asymptote, but a vertical asymptote. Yeah. So at y equals 0, or x equals 0, sorry, that's a vertical asymptote, right? And once again, I can get, as I go closer and closer to 0, I'm going to go further and further up this thing, but I never actually get to the asymptote. Okay? But even though there's no point that's ever on the asymptote, those two asymptotes really are the most important parts of the graph, right? Because they really guide the behavior of the function, even though the function never touches them, right? They're like the skeleton of the function, okay? I could do the same thing, and I'm just going to abbreviate this a little bit so we can get going, but if I were to do the same thing from this side, it probably wouldn't be surprising to see that we're going to get something similar going on. It's going to do that though, right? It's going to be asymptotic on the x-axis, but this time it's sticking to the bottom of the axis. And as it goes closer to 0 from the left side, from the negative direction, it's going to plunge down to negative infinity. Okay, and this is an example, just another very quick review, and you'll see all this stuff again. And that's kind of the way math is, that each time you see it incrementally, you got a few more things to attach the knowledge to, and it starts to really make sense more. A lot of times the first time you see something, you're just not totally prepared for it. But this is an example of a function that has odd behavior, right? Because it has that rotational, odd symmetry, I should say. Has odd symmetry because I could take the entire thing and I could put a pin, a tack in the board at the origin, spin the whole thing half a term, and it lines up with itself, right? So it's got that odd symmetry, okay? All right, so there's our parent function, okay? Not that hard to draw if you know where the asymptotes are, right? Now let's tweak this thing. Let's transform it. Let's take a function like this one, and let's make a sketch of that based on a transformation of the parent function, okay? So remember that in general, if I've got some parent function f of x, then I can always transform that to make a more complicated function g of x by introducing those 4 parameters. What are they? It's one of the parameters that I use to transform a function. A, okay? A, B, H, and K. A is the vertical stretch compression or vertical reflection if it's negative, right? B does the same stuff but horizontally. Stretch, compress, reflect horizontally. What do H and K do? Horizontal shift. And we can think of if we go back to all our parent graphs, each one of these graphs had a special point that we could call it like a vertex or a point of symmetry or something. And it always starts at the origin, right? It starts at 0, 0. So when I shift the whole thing, H and K just become the new coordinates of that special point, right? Where do you think that special point is going to be for us? I mean, I can see there's a couple legitimate possibilities. You might say that point right there, but I don't like that because that point right there sort of neglects the other half of the function. It says this one's more special, and it's really not. What's the point that we probably really want to use? The origin, once again. Even though the origin is not on the function, it's still arguably the most important point because that's the place where the two asymptotes cross, right? So that's the one that we'll track. That's the one we'll always start with when we make our functions. We'll start with the asymptotes and build the function from there, right? Okay, so where does the A go? In front of the F. That goes in front of the whole thing, right? Okay, where does the B go? Where's that go? And well, where's the B go? That's a little tougher one. Okay, so outside, right, there's an X there, isn't there? So it goes outside the X, outside that, and it's the reciprocal, right? It's actually 1 over B that goes out front. Where's the H go? Angelica, where's that go? Remember? Minus H. Right, minus H. So inside here it's X minus H. And now how about the K?
Right on the outside.
Yeah, on the outside, plus K. There you go. Good. All right. So our function, this is just totally general. Our function is 1 over X. So what's that going to look like for us then? G of X equals, well, the A goes out front always, right? So we just put that by itself out front. So I get A times, and then my function is 1 over something, right? It's 1 over X. So where does the B go again? It always goes in front of the X, right? So this is a little odd, but the B goes then on the bottom in this case. It's got to be in front of the X, right? So the 1 over B goes right there. And then I'm going to always subtract the H from the X in parentheses, right? And then at the very end, outside of everything, I just add a K. Does that make sense? So that's what it would look like for this parent function, right? So then all we've got to do here is just recognize what are the values of A, B, H, and K. Okay, what's A? 3, sure. It's the number out front, isn't it? So this tells us A equals 3, right? Is there a B? There's not this time, is there? There's nothing inside the function in front of the X, right? So we can ignore that. B's 1. We don't have to worry about it. How about H and K? Tyler, what's H? You're almost, it's the number that's being subtracted from X. So what is it? 1. There you go. Good. So H is 1 and K is 2. Good. So this is really easy to do then. This tells us that the coordinates of the special point, HK, are 1, 2, and A is 3, right? So what do we do then? Well, we're just going to, let's start with the special point. That goes over 1 and up 2, so there it is. Now, what does that point do for us again on our parent graph? That's the place where the vertical and horizontal asymptotes intersect, right? So when we want to graph this function, this is a little odd, but the very first thing we do is not start on the function. We're just going to build the asymptotes, right? So we're going to draw a vertical asymptote, and a lot of times, I always draw them as just a dashed line, right? It's not part of the function, but it guides the function. And then we draw a horizontal line through that as well. And so there's the skeleton of our function, right? Now normally, where would our point be relative to the intersection point that we start with? Over 1 and up 1. Good. So normally we would go. Normally we would go over 1 and up 1. So that would be it. But A is 3. So we got to stretch that by a factor of 3. So now instead we're going up how far? Well, we're going up 3, right? Because we're saying from that point, what does it mean to stretch something by a factor of 3? It means I'm multiplying it by 3, right? So like let's say a tree is 3 feet tall, and then next year it's 9 feet tall. It's 3 times taller, isn't it? Right? Because it's 3 times 3. So in this case, instead of being 1, it's going to be 3 times 1, which is 3. So it's going to be right there, right? And so if that's the point that's to the right and up, then that means that the function, from there, we're just going to make a sketch. It's got to go through that point and then gradually bend down to the other axis. So what did that do? It pulled it a little bit further away than it normally would have been. The function normally would have looked like that. It just pulled the function a little bit away from the origin, right? But it's still eventually going to stick to those asymptotes. Okay? What about the other direction? Instead of going, normally we would start at the intersection point and go back 1 and down 1. But this time if we're stretching it vertically, instead of going down 1, we're going down 3. So we're going to go down 1, 2, 3 right there. And once again, that's what our function is going to look like. Okay? Does that make sense? Okay? I forgot to mention one thing to you. This isn't a big deal, but I told you that this function is used to model, like let's say that we're producing, I don't know what we're building. We're building, I don't know. We're building barbecues, right? We're going to sell barbecues coming up on summer. So if we want to calculate our production costs, how are we going to make the average cost per barbecue that we manufacture go down, do you think? How is that going to be impacted by the number of barbecues we make? If I manufacture more barbecues, what's that typically going to do to my cost per barbecue? It's going to go down, isn't it? Right? Because I've got economies of scale. It means all the special welders I had to buy, and all that stuff, I only buy it once. And so the more barbecues I have, that one expense gets spread over more barbecues, right? And so do you see that this is really the kind of function that would sort of guide economically, that would sort of guide your thinking about what your production costs are going to be, right? For one of them, or for a really small number of them, the cost is high. But as we increase the number of items, the cost is never going to go to 0, right? But it's always going to go down a little bit, okay? How about one like that? Last one we'll do. Maybe. Might do one more. Let's see. How about this one? Once again, that's just going to be, we can see that's the parent function 1 over x. All we got to do is just inspect that thing and determine what are the values of the parameters, and then the values of the parameters allow me to draw the transformed parent function. So tell me something about that. Everett, tell me something. What's the value of a parameter there?
What?
Say it again.
What?
Tell me the value of a parameter there, of a, b, h, k. Tell me something.
A is 2. Right?
Okay, not quite. Not quite. Something, that 2, where is that 2 in this case? The 2 is inside the function, and it's being multiplied by x plus 3. This is kind of a tricky one, right? So, yeah, so that's the value of actually 1 over b, isn't it? Right? If we go back and we look here, we said that 1 over b, the reciprocal of b always goes in front of x. So for our parent graph, it's going to go on the bottom in front of the x minus h part, right? Okay, so then that's telling us that if 1 over b equals 2, what is the actual value of b? If 1 over b is equal to 2, the reciprocal of b equals 2, then b must equal 1/2, right? Okay, so there's one thing I know. What about, let's see, I want to know, Brooke, what's the value of h and k? Okay, so -3 and, say it again? And, did you say +1 or -1? -1, there you go. So -3 and then plus -1, right? Okay, so then to graph this thing, what are we doing this time? Start off with, we're going to start off with the intersection point is at HK at -3, -1, right? And so that's where the vertical asymptote and the horizontal asymptote intersect, right? Now this time, if b equals 1/2, that's a horizontal stretch or compression. It's going to be a compression, isn't it? Because I'm going to multiply the horizontal distance that I would normally be by 1/2 to draw it in and make it closer to the asymptote, right? So normally, I would go over 1 and up 1. But if I'm going to horizontally compress that point, right, relative to where we started from, instead of going over 1, I'm only going over 1/2 to get there. See what I'm saying? Okay? So that's going to put that point right there instead. Everybody see that? Okay, instead of going back 1 and down 1, normally I would go back 1 and down 1. This time I'm going to go back how far when I go down 1? If I'm horizontally compressing it, only half as far, right? So I'm going to go back 1/2 and down 1 and be right there. Okay, so what's that do to the graph then? If I draw this thing, it's just going to do that, right? So it's just pulling it closer to the origin. It's kind of sucking it in towards the asymptotes, right? Okay. Now there is something interesting going on here that I kind of want you to see, because you can make a choice. This is a really highly symmetrical function, right? We could also write this in a slightly different way. If we write g of x is 1 over 2 times the quantity x plus 3 minus 1. Well, what about that 2? I could factor out a 2 on the bottom, right? Because when I multiply fractions, I'm just multiplying straight across. So do you see that I could also write this, if I want to, as 1/2 times 1 over x plus 3 minus 1. You get that? Because now if I multiply fractions, I multiply straight across, I'm going to get 1 on the top and 2 times the quantity x plus 3 on the bottom. So what'd that tell us? This doesn't look like b now. What's that look like? That isn't being multiplied by something on the bottom, that's being multiplied by the whole thing. So what value, what parameter does that now look like if I factor it out front of the whole thing? A. So it's the same thing as saying a equals 1/2. Think about that. B equals 1/2 means a horizontal compression of 1/2 turns out is identical to a vertical compression of 1/2. Kind of makes sense. If I'm going to suck this thing in towards the horizontal asymptote, aren't I also sucking it in towards the vertical asymptote? Right? It's going to do the same thing, isn't it? I could also think of this as going over 1 and up 1/2, or back 1 and down 1/2. I mean, you don't have to do it that way, but it's just interesting that you can treat it that way. If you'd prefer, whatever the number is on the bottom, I could factor it out and make that 1 over that number the value of A. Okay? Make sense? All right, so last step, and we're there. And then we're done. So what about this? What if we had something like this? I'm going to make a new function here. Let's say we have g of x equals 2x minus 3 over x plus 4, something like that. We want to get a sketch of this. Okay, this is a rational function. This doesn't look like what we just dealt with. Okay, but whenever you have a rational function that is a linear factor divided by a linear factor, right? So there's only one x on the top and one x on the bottom, right? Polynomial, I get a linear polynomial, something times x plus something over something times x plus something. I can always rewrite that to look like the parent function 1 over x that's been transformed. Okay, how do we do that? Well, we just divide. I literally just divide out that fraction, and the answer I get is going to look like a transformation of 1 over x. So there's a couple ways I could do this. We talked about dividing polynomials. I could use long division. That's fine, I could. But this is one where I could use synthetic division instead, right? Because the bottom is linear, and it's easy to spot the 0 of the denominator. What is the 0 of the bottom? -4, right? So I could use synthetic division here and put a -4 in the box. What are the coefficients that go up top then? What would that be? 2 and -3, and there's my remainder box. Okay, so what do we get? If I drop the 2 down, what do I do next? Multiply. 2 times -4 is -8. I add, and what's the remainder? 11. Okay, so that's telling us then, this is the constant, the next number over would be the coefficient of x, etc. Right? Yes, ma'am?
How do you get 11?
Because I'm going to, negative, sorry. Thank you. Is that what you were wondering about? Yeah, -11. So then this is 2 plus the remainder of -11 over the denominator, because that's what the remainder means. It's what remains over the denominator, right? So this looks like 2 plus -11 over x plus 4, right? Let's flip that around. Let's put this term first. So what if I write that as -11 over x plus 4 plus 2? Whatever the number is on top, let's just factor that out front, right? Because that's really the same thing as saying, wouldn't you agree that's the same thing as saying -11 times 1 over x plus 4, right? When I multiply fractions, I multiply straight across, right? You see that? Plus 2. Well, that looks familiar, right? That looks like a transformation of 1 over x, doesn't it? So what are the values of a, h, and k here? What's a? -11. What's h and k? H is -4, k is 2. So if we were to sketch this one, then it's just going to look like, I'm going to go back 4 and up 2. So there's the special point, right, where the asymptotes cross, and that's has coordinates -4, 2. Okay, if a is -11, what's that mean? Instead of going over 1 and up 1, what do? When I go over 1, instead of going up 1, there's 2 things going on. It's negative, so what's that mean? What's that mean? If I go, normally, if a is 1, I go over 1 and up 1. What does a negative value of a do? It reflects it, what's it do? Reflects it vertically or horizontally? Come on now, a is negative. Vertically, right? Well, look how that's consistent with how we're treating this. If I go over 1, instead of going up 1, I'm just going to multiply it by -11. So I'm going down, right? I'm going up -11, which is down 11. So I go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So clear down there, right? And when I go back 1, instead of going down 1, I'm going to do the opposite. I'm going to go up 11, so it's clear up there. So what'd that do? it just made this thing, it just pulled it a long ways away from the asymptotes, right? But that's what the graph's gonna look like there, okay? Where's that? Let me clear up here somewhere. So anyway, it's doing something like, right, we got it?